So we've been talking about uh, putting functions together by adding, subtracting, multiplying, dividing. So we'll just look at a few applications of this. So this first example says a local hockey team owner would like to boost fan support at games. He decides to reduce ticket prices T in dollars according to this function. T at G equals 10 minus 0.1 G, where G represents the game number. So T is the ticket price in dollars, G is the game number. To further increase fan support, he decides to randomly give away noisemakers. The number n in hundreds of noisemakers can be modeled by this function, again as a function of G, the game number. N at G equals 2 minus 0.05 G. The community fan base is small, but the owner notices that since the incentives are put in place, the attendance A in hundreds can be modeled by this equation, again in terms of G. A at G is 8 plus 0.2 G, so G is a game number. The first thing it asks us to do is determine R at G, which is T at G times A at G. So T at G is the ticket price, A at G is the attendance. So if you multiply the ticket price by the attendance, what does that give you, Leo? It gives you your revenue, how much money you take in. So that's why the letter R at G is being used. It will represent the revenue. But first we need to write that expression. R at G, it says, is T at G times A at G. So T at G is 10 take away 0.1 G times A at G, which is 8 plus 0.2 G. And I mean, you could definitely multiply those out. You'll get 80 when you multiply the front terms. The outer terms will be plus 2G. The inner terms will be negative 0.8 G. And the last will be negative 0.02 G squared. So this will give us negative 0.02 G squared plus 1.2 G plus 80. And again, this is our revenue function. Right, so that's part A done. Then we're asked in part B to use the graph to determine whether the owner increases or decreases revenue from the ticket sales with the changes made to draw in new fans. So we will use the calculator to do this. Put this equation into y1, and you could put the original factored form in or the simplified one, it won't matter. So negative 0.02 x squared plus 1.2 x plus 80. And I will use zoom fit, zoom 0. Calculator will pick the windows, and it's a quadratic because the initial term, or the highest power, is 2. So it is a quadratic, and it opens downwards because that initial term is negative. Now we might adjust our windows a little bit. I don't think our y minimum needs to be quite so small. We're not concerned with negative values for revenue, which is what you would get when you go below the x-axis. So my windows, maybe I'll change my x value starting at negative 10 to 200. We can keep the scale there, but my y minimum doesn't have to be so big. I'm going to go, or so small I should say, I'm going to go from negative 10 up to 100, and let's use a scale of 10 on the y-axis. So I adjusted the windows a little bit. Now when I hit graph, it looks a little bit better. So we can see by looking at this graph that at the start, as the game numbers increase, which is along the x-axis, the revenue is increasing. And it comes up to a maximum, and then it starts to decrease after that. As the game numbers increase, we can see that the revenue is decreasing, but there is a point where there's a maximum, right? So we can find out what that maximum is. Second function trace, number 4 for maximum. I'll put my left boundary at 0 and my right boundary at, say, 50, and then hit enter, and there's our maximum. The maximum occurs at 30, 98. So for part B, we can say that revenue increases to a maximum point and then decreases. The max is at 30, 98. This is our maximum revenue. Now remember that G stands for the game number, and if we look at what A is, it's in hundreds, okay? So on our y-axis, we will have in hundreds. So this means that maximum revenue of $9,800 occurs at game 30. That's what this tells us. So there's part B. And now C asks us to develop an algebraic and graphical model for P at G equaling N at G over A at G. Explain what it means, and then what is the chance of receiving a free noisemaker for a fan attending game 4. So when it asks that question, what is the chance of receiving a free noisemaker when G is 4, it's like asking for the probability. And that's what P at G will actually represent. So let's see why. So part C, again, we want to do P at G. It equals, we are told, N at G over A at G. N at G, which is the number of noisemakers, 2 minus 0.05 G, over A at G, which is our attendance. So that is 8 plus 0.2 G. We know that probability generally is found by taking the number of favorable outcomes divided by the number of possible outcomes. Well, that's what this expression will give us. It'll give us the number of free noisemakers. So this represents the number of free noisemakers that will be given out divided by the number of fans attending. It represents the probability. that a fan will receive a noisemaker as a function of the number of games played. Or we can say the game number. Because again, remember, probability is number of favorable outcomes divided by the number of possible outcomes. So we want to know the chance of receiving a free noisemaker for a fan attending game 4. So this will be P at 4. So we're going to let G equal 4 in that expression. So it'll be 2 minus 0.05 times 4 all over 8 plus 0.2 times 4. So 2 minus 0.05 times 4 gives us 1.8 on top. The denominator will be 8 plus 0.2 times 4. That'll be 8.8. And when we divide these, 1.8 divided by 8.8 gives us 0.2045 repeating. So approximately 20.5% is the probability that a fan attending game 4 would receive one of these noisemakers. Right, and you could look at this in the graphing calculator as well. The numerator in brackets 2 minus 0.05x, close the bracket, divided by in brackets 8 plus 0.2 times x, close that bracket, zoom 0 again. And so we can see by this graph that the probability is the greatest at the start. As the game numbers increase, the probability is getting smaller and smaller. Okay? And if we found the x-intercept of this graph, and if we look at our window, our x scale is 20, so it looks like the x-intercept appears to be at 40. That's where the probability of receiving a noisemaker is 0. And then after that, probability actually becomes negative, which doesn't really it doesn't mean anything in this case. Probability can't be negative. The lowest it can be is 0, right? But we can see that the greatest probability is at game 0, and it looks like the x-intercept is at 40. If we go into trace and let x equal 40, yes, y does equal 0 there. So after that, there is no chance of getting a noisemaker, right? Okay. Next question says, a pendulum is released and allowed to swing back and forth. The periodic nature of the motion is described by this function. It's a sinusoidal function, right? It's a graph 10 cos 2t, where p is the horizontal displacement in centimeters from the pendulum's resting position as a function of time t in seconds. Then it says there's a decay of the amplitude. The decay of the amplitude is given by q at t equals 0.95 t. So if you think back to what we learned about exponential functions, you have a base of 0.95, which means that the amplitude is always decreasing to 95% of what it was before the previous time, or it's decreasing or decaying by 5% each trip. That's really what it means. A asks us to write the combined function that is the product of the two components and explain what this represents. So for part A, the combined function that represents the product of these two functions would be P at t times Q at t. And so what this represents, if you multiply these two together, it represents the actual distance of the pendulum from its resting position. And because the variable is t, it's as a function of time. And when we say the distance, it's the horizontal displacement. That's what it is, right? Because that first formula represents the horizontal displacement. The pendulum's going back and forth, right? So its horizontal distance is what's being measured. And it slows down or it decreases that distance over time. And that distance, that decrease factor is 0.95. It's 95% of the distance it was in the previous cycle, if you want. So part B says, graph the combined function, describe its characteristics, and explain how the graph models the motion of the pendulum. So back to the calculator we go. In this case, because we're graphing a trig function, we need to be in radians. We're always in radians unless we're specifically told that something's been measured in degrees. But in this case, we are in radians. So 10 times the cosine of 2x in brackets, and that's multiplied by 0.95 to the power x. So there's that equation. Now, when we look at the graph of 10 cos 2x, that's the graph of cos x with an amplitude of 10. So it's going to go up to 10 and down to 10. The 2x part means that it's going to be horizontally stretched by a factor of a half, right? So instead of having a period of 2 pi radians, the period of one cycle will be pi radians. That's what that graph will look like. But then it's being multiplied by 0.95 to the power x. So that means everything, that amplitude, everything's going to be decreased by 95% of what it was before. So the amplitude is going to get smaller, right? So 10 should be the maximum amplitude. So we can try zoom 0 and see what we get. Looks pretty cool. So it is kind of doing what we thought it would do, and that is that the amplitude should be at 10, and then it's decreasing to 95% of what it was the previous cycle. This also tells us that whatever windows the calculator chose, it looks like the Y windows are fine, but the X windows are likely a lot larger than they need to be. So our X goes from negative 10 to 200. Our Y goes from negative 6 to positive 6. I'm going to go from negative 10 to, let's just say, 50 on the x-axis. I'll change my scale to 10. And I'm going to go from negative 10 to positive 10 on the y-axis with a scale of, let's say, 2. So now when I graph it, it looks a little bit better. Right? You can clearly see that sinusoidal shape of the graph. Right? So again, this represents, or when we describe what's happening here, so the amplitude is decreasing from a maximum at time 0 to a minimum value. And I mean, technically, when you multiply something by 0.95, it's never going to be 0. even though this pendulum would look like it has stopped, when you multiply something by 0.95, you're never actually going to get zero. It'll approach zero, but technically never actually get there. So when we describe what's happening here, we can say the displacement is at a maximum at time zero and decreases by 5% after each cycle. Again, it's maintaining 95% of its displacement. That's what the 0.95 tells us, which means it's decreasing by 5% after each cycle. So that is what's happening. All right. The next one says the number n of bacteria in a refrigerated petri dish is given by this function. N at t equals 20t squared minus 80t plus 500, where t is between 2 and 14. T is the temperature of the petri dish in degrees Celsius. When the petri dish is removed from refrigeration, the temperature of the petri dish is given by that second formula. So n is the number of bacteria in terms of T, the temperature. T, the temperature in terms of T time in hours, little t in hours, is 4T plus 2. We want to find the composition of n at T and T and interpret its meaning in context. Now, this composition of functions is what we're going to be talking about in 10.3. But you did learn about this in 20-1, where one function is embedded into another. So you did see this in 20-1, so this example will serve as a bit of a refresher on how that works, but we'll look at it a little closer on Monday. Okay, and then that is the end of chapter 10, which means Tuesday you'll have a quiz on chapter 10, and then we'll be starting chapter 11 on permutations and combinations. At the end of chapter 11 is when we'll have our last unit exam, and then we'll start reviewing for the diploma exam. Okay, so let's go through this one. Find the composition n at t at t. So this is where one function's embedded into the other, and you work your way from the inside out. So this means that capital T at t, which is your 4t plus 2, is embedded into function n. Wherever the variable is in n, which is capital T, you're going to replace it with 4t plus 2. So it'll be 20 times 4t plus 2. Whatever happens to the capital T in that original equation happens to our new one as well, which means that it's squared. Minus 80 times 4t plus 2 plus 500. So when capital T at t, which is the time function, is embedded into the number function, this represents the number of bacteria as a function of time. So this represents the number of bacteria as a function of time, because that is the variable that's in the equation. You see, the original formula for n was as a function of T, the temperature, since it was removed from refrigeration. Our new one, it's a function of time in hours, right? So there's that formula. And you could definitely simplify it. You could square the 4t plus 2 and multiply by 20. You could multiply the 4t plus 2 by the negative 80 and add the 500 and simplify. You could do that. Not really necessary, though. Part B asks us to find the number of bacteria after 2 hours. So this will be n at t at 2. So we can just simply let t equal 2 in this equation. So as I said, you don't really need to simplify the equation. You can just work it out by letting little t equal 2. And get your answer that way. So 4 times 2 is 8, plus 2 is 10. 10 squared is 100, times 20 is 2,000, minus 4 times 2 is 8, plus 2 is 10, times 80 is 800, plus 500. 1,200 plus 500 is 1,700. So that's how many bacteria are there after 2 hours. Okay, and part C, find the time when the bacteria count reaches 2,000. So using that formula that we have above, our new one, we're going to let n, the number, equal 2,000. Whoops, not equals 500 plus 500. So we want to solve this equation. So we can subtract the 2,000 from both sides to make it equal to 0. Which will give us minus 1,500 on the right when you subtract 2,000 from both sides. And now we can look at this equation in terms of a quadratic, right? We can take that 4t plus 2 and let it equal some variable. Let's say the variable x. If we replace the 4t plus 2 with x, this equation becomes 20x squared minus 80x minus 1,500 equals 0. So we've simplified that expression, that quadratic equation, into something that we can work with. We solve quadratics normally by factoring. So let's see if we can factor this. Common factor of 20. I think that's 75, 1,500 divided by 20. Yeah. Now, unfortunately, that quadratic that's inside the brackets cannot be factored. There are no two numbers that multiply to get negative 75 and add to get negative 4, so we will use the quadratic formula. Again, we're factoring the quadratic inside the bracket. Our b value is negative 4, so negative b will be positive 4, plus or minus the root of. B squared will be 16 minus 4 times A times C all over 2A. So our radicand, 16 take away 4 times 1 times negative 75 is 316. And so we can't get a negative value for x because that means 4t plus 2 is negative. T is time. Can't have a negative 1. If you take the root of 316, you get approximately 17.8. If you go 4 minus 17.8, you're going to get a negative value on top. So we can't have that. So it'll only be the positive value. So we'll add 4 to that. 4 plus that divided by 2. So x is approximately 10.9. That's an approximate value for x. But remember, x equals 4t plus 2. So we're going to put that back in. So now we can say 4t plus 2 equals that approximate value of 10.9. And we'll solve for t because that's what we want to know. What is the time t where the number of bacteria reach 2,000? So 4t will equal, and again, we want to keep this number in our calculator. So I've got that decimal there. I will subtract 2 because I'm subtracting 2 from both sides. So 4t will equal approximately 8.9. And then we'll divide by 4 to get our approximate answer. So divided by 4, so approximately 2.22 hours is how long it would take for the number of bacteria to reach 2,000. Okay? So for practice, there's just a couple questions to work on. Questions 12 and 13 on page 497. And so again on Monday, we'll look at composition of functions where functions are combined. And we should be able to get through that all on Monday, which again means that Tuesday, you'll have a quiz on chapter 10. We'll also be starting our last chapter on permutations and combinations. And then after that will be our last unit exam. And then we'll be reviewing. And then as we go through that review process, there'll be a chance to write the other rewrites that we haven't done just because of timing. Okay?